Morning, everyone. We'll start in a moment. There's still a couple people not on. Being the first time, I'll give them a little time. And also, my program is I had quantum mechanics this morning, and it's converting the lecture to video on my computer, and it's taking actually remarkably long because the file's enormous. I can't wait to find out the size. It's going to be way in the gigabytes. There's a good chance I may not be able to actually record these. I honestly don't know. Today I'm going to find that out. I'm going to go start in a couple more minutes. We have actually a pretty good group. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of you, which is actually not that bad. I think there'll be a handful more, probably like 2 or something, 1 or 2. Give them a minute. Morning, Justin.
This is 125.
126. So we're gonna do Bielsa Verbal today. Okay, so I'll get my coffee, then we'll start. I'm probably gonna have to pause in a moment because the one file is almost converted. I went a little long in quantum mechanics today, longer than I thought. And so I wanted to have the conversion all done before the class started, and it's only 77% converted. Probably about 3 more minutes or so, and I'll be converted. Okay, so let me get my coffee, and we'll go from there.
What day is today?
Today is the 24th. Yeah. Okay, so we can start. And I'm going to probably toggle between 2 things here. Let me open up a second screen here. And the computer keeps on telling me that my internet is unstable, which I know that. This is here. Okay, that's looking pretty good. So, we're doing magnetic fields. I hope you've been following all the lectures up to this point. If not, go watch them as soon as possible. Let me do a little bit of review here, not a lot of review, and then I want to get to something new. I want to show you how to calculate magnetic fields. And this is something called the Biot-Savart law. So we have 2 right-hand rules. Did I not let you in?
It's working on it. Continue. Probably
Okay.
fine.
Actually, I don't think I sent you some. Hang on. My daughter is taking the notes for this class, and I do not think I sent her the invitation for this. Somebody just came in. And where are, is that you, sir? Or is that?
No.
Okay, I've lost something. I can't seem to let that person in. You're gonna have to bear with me while I try to get this all straightened out. Okay. Okay, could you actually just read on?
Yeah.
Okay, so Sarah's just going to, I'll send her, make sure she has a link. Normally, I will just, she'll just have to look at the angle today. Okay, so we have two right-hand rules. What were they? What was the first one? And why don't you, some of you can chime in and let me know. So what are the two right-hand rules we had? You can just unmute yourself and then tell me, or one of you can, or a couple.
One was the direction of a magnetic field.
Okay, how did we find it? So we had a point charge here with a velocity here v, or we had a wire with a current here I. What did we say happens? How do you find the magnetic field in each of these cases?
Is it F equals QV cross B?
Yeah, so we're gonna have two here. This is one of the rules. This is gonna be our cross product rule. Okay, that's one of them. And this is gonna be the standard cross product rule. Your fingers go in the direction of V and your fingers cross in a B, like that. That's one of them. Then the other one is, what do we do up here? And it is for finding B. How does this one up here go? For some reason, my camera is.
It's thumb in direction of the velocity or the current.
Good. So you point your thumb in the direction of the velocity here, and your fingers wrap in the direction of the B field. So in the first case, in this case here, I'd go like that. My thumb's going this way, my fingers wrap up here. So the field would be coming out on this side and in on this side, like that. And in this case here, if I had a wire with current like this, now let me put it over here. If I had current going that way, I'd grab hold of the wire like this, pointing my thumb in the direction of it. So imagine you just grab hold of that wire. Your fingers go like this. So it comes out on this side and then on this side. Okay, that's one of them. And the other one, somebody already said, is this F equals QV cross B. So let's do an example here. Let's say I have B coming out here like this. This is B. And let's say I have a negative charge going that way. What's going to be the direction of the force on this point charge here? Up, down, right, left, in, out.
Down and to the right.
Down and to the right. People believe that? It's saying kind of down that way. Believable? Not believable? I believe it.
Believable.
Yeah. So let's do V cross B. So where do your fingers go first? Along the direction of the first vector. This is B. So my fingers go that way. B's out of the page. So V cross into B. That would be a force going like that. But why do we have to flip it? This is actually correct. Why does it get flipped?
The negative charge.
Perfect. You have this Q here. That Q becomes negative and that flips just like this. Okay, so we have that. Then we had another one too that we derived last time. We said, let's say we have an external B field like this. I could have a wire in it with current maybe like this. And we wanted the force that this B field puts on the wire. Remember what we said is we said, well, we don't know what the force is for this, but we know that this expression here, this is the force on a point charge. Okay. That's the force on a point charge. And so what we did is we took this current going like this and we broke it up into a whole bunch of little point charges like this. And we could find the force on all these. So what we did, we said we actually, to make this a little more user-friendly, we drew a little kind of section here. We said that the charge for this guy is dq, and the velocity of this guy here is v like that. And so I could apply this here. So we did our V cross B, so our V's that way, or B's that way. This is a little force on this guy. And it's only the force on that little fellow, and so we had to call that force dF. So that actual force was dq times the velocity crossed into B. And then what did we say about this velocity here? Well, we know velocity is dx dt, and so I think we called it dl last time. Did we? Well, we're going to call it dl today. So we're going to say that this velocity, if it's moving this way, is going to be some dl dt, and that dl, that's going to be a tiny little piece along the same wire here that it's moving. So I could put that in here. So that gives us df equals, if you have to move search to kind of get this, this is fine. This is dq, dl dt cross B. We said this right here is our friend. We call that the current I. So we sort of df is I dl cross B. But that's just the force on this little guy here. So if we wanted the total force, we had to add up all the little contributions here, which meant that we had to do an integral. And the integral was a little funny. I could pull the I out here. And this B we're assuming is constant, so I can pull this out on the right side of the integral. So I'll put it like a bracket there. So that indicates that I pulled that B out of this side here. And my computer is telling me my internet is unstable again. Okay. This guy here, if you take a DL and sum them up along the entire length of the wire, you get L. So this is your I, L cross B, and that's your total force. And that's where that one comes from. So now let's go back to that problem, find the direction for it. And then I want to show you.
Don't erase the last part.
I won't.
Thank you.
So again, that's my daughter's voice, if you're wondering who that is.
Hello.
So here's our I, here's a B like this. So from this expression here, what would be the direction of the force on this wire? Up, down, right, left, in, out?
Up and to the left.
I'm hearing up and to the left, going that way. Confirmation. Okay, my daughter is giving you thumbs up. Yes. L, crossing the B goes up like this. And what do you know about any cross product here? Remember, this is a result of a cross product. Any cross product must be perpendicular to the two vectors in it. B's into the board. L is always along the direction of the current. So this force here is perpendicular to both this and that. So that works. So what I want to do today is we want to start doing more technical stuff. So I want to start dealing with finding magnetic fields. So I want to talk about how do we find B fields. For some reason here, my camera is looking actually fuzzy, and I don't, I'd fixed it this morning. Let me try something really quick. I'm going to try to focus the camera. It was fine in quantum. I'm also having allergy problems, so I'm having constant water go down my eyes. Just bear with me for a moment. Okay, is that better?
Yes.
Okay. Again, if it goes out of focus, let me know. I can most likely fix it. So my camera changed on me. This is interesting. Like that. Let me do something here. I lost something. Okay, they're back. Sorry about that. Okay, so we have two ways here. The way we're going to do today is something called the Biot-Savart law. Okay, these are two different people. Biot is French, that's why it's not Biot. The OT is silent, so it's Biot. I don't know for a fact, but I think the B here is why you actually call magnetic fields with a B, although I don't know that for a fact. That's my conjecture. I think this is where you get it. That's going to be one way we're going to get magnetic fields. The other way is going to be Ampere's law. Okay, so we're going to do Ampere's law probably on Friday. Today we're going to do Biot-Savart. Tomorrow we're going to do more examples of it. Biot-Savart problems you're going to love. They're going to look absolutely awful. You're going to look at these things and say, I can't do that. They're too complicated to do. And once you learn the little trick, it turns out these are all beautiful problems. Ampere's law is going to be a little more subtle. This is going to be another one of Maxwell's equations. You don't know that yet, but I'm going to tell you that. And so these are the two techniques we're going to do for a while. And then we're going to get a lot of mileage on these. So before we do this, let's do a little review of how we found electric fields. So remember, if I had, this is some charge here like this. This is some arbitrary charge distribution. So there could be positive charge all over this, or who knows, it's something really complicated. And I wanted to find the electric field here. Okay. What was the first way we learned to find the electric field here due to that charge distribution? So what is it? What's the first way we learned? And that's close, we just need some more details. Okay, so since I'm not getting an answer, I'll give it to you. So we took this right here, we treated this as a collection of point charges. We treat as a collection of point charges. And why did we do that? No, do that, because we know the electric field for a point charge. Remember, if I have a charge here Q, if I come out here some distance R, if I want the electric field here E, the magnitude of it is going to be this K Q over R squared. So what I'm going to do here is I'm going to make this, I'm going to erase that and just make it bigger because it's, I'm going to put something in it. Okay. So if I have something like this, I'm going to treat this as a collection of point charges. So I'm going to come over here and draw some tiny little point charge. I call that dq. And then if I want the electric field, then at this point here, I'm going to have this direction here. There's going to be some electric field here going this way. I'll call that dE. It's a vector here. And what does that have to be given by? Well, the magnitude of this has to be K dq over R squared. Now this is a little more complicated because the electric field is a vector. So we need some vector going in that direction here. So what I'm going to do is that if I call from here to there, if I make that a vector so that the magnitude of this is R, but if I make this an actual vector here like this, and say that's R, remember that anything that points along that same direction but has a length of 1 is a unit vector. So I can really say is that the direction here, the magnitude of it, this is going to be the magnitude is this K dq over R squared. So that's the magnitude of this vector, but the direction of it has to be in this R unit vector direction. Remember, a unit vector by definition has a magnitude of 1. If you put a little hat on something, it means it has a length of 1, but it points along the direction of the original vector. So all that means is that the electric field at this point here points along that R vector. If I want the total electric field then for this thing here, I then have to integrate all these little dq's here. So I have to do an integral over this entire object here. And remember that integral became really, really difficult to do in most cases if we didn't have a high degree of symmetry. And my computer is telling me my internet's unstable again. Okay, so, and then one other thing, this K here, remember we had another way of writing K. Remember we had this K, we could write it as 1 over 4 pi epsilon naught. And the epsilon naught was the permittivity of free space. Okay? So what we're going to do is when we do the Beel's-Savart law, we're going to get something that looks a lot like this. But it gets a little, there's a couple things that look a little odd about it. So let's actually set this up. So the Beel's-Savart law, the Beel's-Savart law, is the magnetic analog, okay, of basically the electrostatic equation here, of treating the object as a collection of point charges. Okay, so that's what that's going to be. So I'm going to erase this. I'm going to draw an arbitrary wire, and then we're going to find out how to take this equation here and modify it for our problem. Okay, the expression itself is going to look straight from hell, but it turns out it's going to be actually quite nice, and you're going to really like these problems. They're going to be actually some of your bestest friends. Okay, so the Beelzebub law will allow us to calculate the B field for an arbitrary shaped wire carrying a current I. So we're gonna have some wire here. So imagine you go when you, I don't know, you make some modern art that looks like that. That's your wire. It's gonna carry some current here. So here's my current, it's going through it like this. That current here is I. And I wanna find B here. Okay, the Beelzebub law is going to tell us what to do here. And what we're going to do, we're going to set this up exactly like we did for the electrostatic case. So I'm going to take this wire here, which is this convoluted thing, and I'm going to break it up into a whole bunch of tiny little pieces. So I'm going to go over to, let's say here. So I'm going to break this wire up into a whole bunch of little sections. So I'm going to go over here, and I'm going to draw some little section like this. And erase that, make it a little better. So this right here, that's the tiny little segment. I think actually, I do have colored markers here. I'll try black. Maybe black will show up better. Yeah, that shows up. On my screen, that shows up pretty well. Okay, so this little section here, this little black thing that I drew, this is a small segment of the wire. It's tangent to the current at that spot here. So right here, the current's in that direction, so this DL is in this direction. So I'm going to call that DL vector. Again, what does it mean to put a D in front of something? D always refers to a small quantity. We're treating this in terms of calculus. So we have a small section here. So this DL here, this DL is tangent, okay, is tangent to the wire, okay, and it's in the same direction as a current. Okay, that's what we have. Okay, so I'm going to say from here to there then. Okay, I'm going to say from here to there. Okay, so from this little segment here to the point I want to find the electric field, this is going to be my R vector. And I can connect a little tiny unit vector in that same direction, and that little tiny unit vector pointing in that same direction would be R hat. So the question is, what is going to be the magnetic field at this point just due to that tiny little section? And the Beelzebub law is going to give us that. So let me tell you what it's going to be. Okay, so recall the magnetic case, I mean the electric case. Remember the electric case, we had this dE was 1/4 pi epsilon naught. Remember, that's just nothing, but this is just our K. We're used to writing it as K, but it's also that. dQ over R squared R hat. That's what we had. We're gonna, by analogy, we're gonna go from this equation to get this equation. You can actually prove this from more fundamental physics, but not at this level. This level here, I'm just gonna treat it as a fact. So I'm gonna say the tiny little magnetic field dB at this spot is gonna be what? We're gonna modify this. So it turns out that the distance dependence on the dB goes as the same as this. So this is going as r squared. Now, we still get that 4 pi here. Now this is actually the weird thing. This is one of the weird things. Instead of having an epsilon naught in the bottom here, remember that's a constant, that's our permittivity of free space. Well, the corresponding magnetic case actually goes in the numerator. We call it mu naught. And this right here is your permeability. Of free space. And it's a magnetic analog of basically the epsilon naught. So we had the epsilon naught, the permittivity of free space in the electrostatic case. Here we had the permeability of free space. Now, here's where it gets a little funky here. The problem is we needed something for the dq here. Well, we just can't put an I here, but we know that this has to be related with I. And the other thing is, what would have to be the direction of the magnetic field at this spot just due to that tiny little section of the wire? So I'm going to stop here. What would be the direction of the magnetic field here at this spot? I'll make it bigger. What's the direction of the magnetic field here just due to that little tiny guy here? Why don't one of you or several of you chime in, tell me which direction and tell me how you got it. You're going to have to use one of your right-hand rules. Okay, I'm not seeing anyone, so I'll do it myself. Okay. So remember, we had that one right-hand rule that said if you have a current-carrying wire here.
Going into the page.
Excellent. This is going to have to be going into the page. And again, the way that works is, remember, if you have a current-carrying wire here, like this, what do? You point your thumb in the direction of the magnetic field and your fingers wrap in the direction of B. So if I grab hold of only this tiny little section, my fingers wrap like this. So at this spot here, that magnetic field has to go in here. So this creates a problem here. Notice that r hat here, I just can't, don't write this down, this is wrong. You might be tempted to say, oh, well, I'll just say like I times r hat here like this, and that'll be good enough. And maybe even throw in like a DL or something. That doesn't work. First of all, you may need this tiny little bit here, and this r direction is not the same as this. So somehow we have to do something different here. And this is what you end up doing. What you end up doing is, first of all, this has to be directly proportional to the current. So you need the current here, I. And it does have to relate to this DL here. The problem is that this DL here does not point in the direction of this dB here. But what would? Well, if I take that DL and if I cross that into r hat, remember the r hat here, it has a length of 1. So it's not affecting anything, and it has no units. So if you work this out, if I do the DL cross r hat, let's do this. So here's DL, here's r hat. Let's do our right-hand rule for it. So DL, remember your fingers go in the direction of the first, then you cross them into the second. I'll wait till my internet says I'm no longer unstable. Okay. So DL, crossed r hat, my thumb is going into the board. DL, crossed r hat, thumbs in the board. That's how that works. So the odd thing here is that this whole quantity here, this IDL cross r hat, that's really the analog of that DQR hat here. That's kind of the weird thing. So that's very odd. But this whole law here like this, in this form, that's the Biot-Savart law. And that's what I want to do today. I want to do one example of it today. And then we're going to do just nothing but examples with it tomorrow. again, you look at this and you think, oh no, the class is over. No, this equation is going to become your bestest friend. You're gonna learn to love that equation. So I want to say a little bit more about that today. And I'm going to give you a lie that's not that bad of a lie, but I'm gonna lie to you today, and I'm going to tell you where it is. I'm going to lie to you right now. So I'm going to say the Beelzebub law. Again, that's our dB equals mu naught over 4 pi I dl cross r hat over r squared is always true, and I've just lied to you there. In fact, I'll say this is a lie. Now, the reason why I'm going to say it's always true, because basically by always true, I mean it's always going to be true in this course. I'll never give you a problem where basically this law falls apart. There's something called magnetostatics. I don't want to get into a whole lot of the magnetostatics case, what exactly it means. It's actually a little more subtle than I want to get into, but it turns out that we're going to be dealing with magnetostatics in this course. And it turns out that this will always work for magnetostatics. So by always true, I mean this law here will always be true in this case here. Okay, but just so you know, okay, that I just did tell you a lie, but it's not that bad of a lie. Now, so although the Beelzebub law is always true, and again, I'll put true in quotes, it cannot easily be applied in most cases. So although I could give you a wire like this and say like that, here's I, and say find the magnetic field there, right at this spot here. You could do that. What you'd have to do though is you'd actually have to put this equation on the computer and do this problem numerically. That would work. Now, where you can apply it is actually in two cases here. And so, however, we can apply the Beelzebub law, and just start calling it BS. No jokes. Okay, the BS equation law in two cases. These two cases are one, long straight sections. Actually, they don't even have to be long. They just have to be straight sections. They don't have to be long. Straight sections. Of wire. Okay. And circular sections of wire. Okay. Internet says it's unstable again. So let me give an example here. Suppose I give you a long straight wire here, so that's long. Imagine it comes in from infinity, although it doesn't really have to. You're gonna have a curvy spot here. So this has some radius here, r. It goes like that. So I have current coming in like this. Okay. And the only spot we're gonna easily be able to find the magnetic field is here. Right there. I want you to find, oops, that's getting too close to the end here. I want you to find B here. Okay. What I want to show you is that you can actually do the Biot-Savart law for this problem here, and it's going to work actually quite easy. And so I want to show you how to do that. And let me check the time here. I'm going to end this a little bit sooner than normal, because basically I want this to have enough time to save for my next class, but I will now adjust things so I know what to do. There's a learning curve for me here today. I'm learning just as much about this technology as you are. So we're going to go, I'll stop probably abruptly at 10:05. And I will do that with my quantum class as well. And so there shouldn't be a problem from now on in. So, okay, so how are you going to do this? So again, the indication that this is going to be a Biot-Savart problem is I have a section here, this is straight. I have a curved section here and a straight section. When you have those conditions here, that's always going to be Biot-Savart. So let's see how this works. I'm going to make it bigger up here. So it's the same picture, you don't have to redraw it. So we have that. And I want to find B here. Again, you're going to love these problems once you get used to them. Okay, to do this here, what you're going to do, you're going to break this up into 3 sections. So break into 3 sections. The reason you're going to do that is we have one section here, that straight section. We have this curved section here too, and then we have that straight section here. So I'm going to say the total magnetic field. That's the total magnetic field at this point here. Let's call this point P. I'll just call it here. So this is the total magnetic field at this point here. It has 3 contributions to be from the first wire, this wire. So there would be some magnetic field at this point from this wire. Plus a magnetic field from the second section. In other words, this curved here will have a magnetic contribution here. And this section here is going like that. That will also have its magnetic field. So that has to be the magnetic field. Okay, what I'm going to do is let's look at this one here. Let's look at section B1. I want to find the magnetic field here. So what is the Biot-Savart law? Well, again, remember the Biot-Savart law is dB equals, not that at all, mu naught over 4 pi I dl crossed r hat all over r squared. And when you do these, always draw what these are. If you draw what they are every time, everything is going to be really easy. So I'm going to go over here. So I'm just going to look at, concentrate on this section here. So here's my wire, that's section 1, and here's my point. So if I were to say, draw this, what would you do? Well, through the miracle of the black pen, I come over here, I draw my tiny little section here, DL. Now, why does my DL go in that direction? Because the current's going in that direction. Remember, DL is tangent to your wire, but it points in the direction of the current. And then where does my R vector go? Well, my R vector starts here to that same spot and goes here. That's my R vector. So where's my R unit vector? Well, my R unit vector has to point in that same direction, but it has a length of 1. So what would be DL? What is DL crossed R hat for that section here? So I'll stop here and let you guys chime in. So what is this for that part here?
Should be 0.
Exactly. Again, the reason why is if you look at the magnitude of this is magnitude of DL, magnitude of R hat, times the sine of the angle between the two. Well, R hat and DL make no angle, that's 0. So this is 0, this is why this is 0. So there is no contribution from that first section here. Now, we'll do one more section, and then we'll call it quits for the day. Let's look at this section here. What's going to be the magnetic field at this spot due to section 3? What would it have to be? 0, right? Here's your DL vector. Where does our vector go? It goes from this point to the point in question, so this is our vector. So how does the R unit vector have to go? Well, it has to go along the direction of R. So now these two make a 180-degree angle here. So again, if I write down my Biot-Savart law, like that, if I look at this guy, I look at the magnitude here. What is that? Well, that's magnitude of DL, magnitude of R hat, times what? Well, you need the sine of the angle between the two. Well, the angle between these two is 180. Sine of 180 is 0, so this is 0. So the only magnetic field coming from this weird shape here is going to be the magnetic field coming from that. And what we'll do tomorrow is do that. And then we're going to do some other ones too. Don't write this down because we'll do it tomorrow. Suppose I give you something that looks like this. I want you to find the magnetic field there. Or suppose I give you something like this. I want you to find the magnetic field there. Or suppose I give you something like this. I want you to find the magnetic field. Ooh, can't see that. I want you to find the magnetic field there. These are all weird shapes, but it turns out we can do the Biot-Savart law, and we can actually calculate those magnetic fields really, really easily. So what we're going to do, we're going to finish up this one tomorrow, and then do this one, and do this one, and then do this one. And probably some other ones as well. And again, these look awful when you first see them, but they're going to be your bestest friend. So I'm going to stop very abruptly right now to stop this so it can be saved, because I'm going to my 125 class immediately after this. I will have office hours this afternoon. So feel free to just send me an email, and we can set up a little section, or I think I'm just going to set up a generic section. I don't quite know how my office hours is going to work yet, but I'm going to be here to answer your questions if you have it. So have a great day. Let me know how this works. It's not at all the same as being there, and I apologize for that. I don't know what else to do though. So have a great day. I'm going to pause this now, and see you later. Assuming I can do something here. Okay, now I'm going to end the meeting. Have a great day. Bye-bye.